Titrations are a very common wet chemistry activity, and they're pretty practical in a real laboratory setting as well. One of the things that we look at in the big picture is how does a titration curve work and where do these numbers come from, and also how can we make predictions along the way. And technically this is a little artificial because I'm pretending we know some of the information, but this is a typical type of calculation. The first thing we need to glance at is your typical pH titration curve, and we're just going to say we have like a strong acid with a strong base. All right, and in a different video we talk about like why they look different for strong acid with strong base and weak acid with weak base, etc. But the generic curve you might see is something like this, up and then over like that. And of note for strong acid with strong base, we have this point right here, which is our equivalence point. And that equivalence point happens at pH 7. All right, and then we've got some equivalence volume there. Everything before that equivalence point is acidic due to excess acid. And everything after that equivalence point is basic due to excess base. And that's a typical titration curve for strong acid with strong base. What I'm also going to do with these calculations, this is part 1 of 3, we'll do the stoichiometry in this video, then in the next video we'll calculate the pHs for this titration curve, and then in the third video we'll compare that to how it looks for a weak acid titration with a strong base. And you tend to get a shape something like this, which is a little bit exaggerated, but it's good enough. Same axes there, base and pH, but this one is weak acid with strong base. All right? And you end up with a special region right there in the middle. You still have some acidity, but right here we have this buffer region, as we'll find out. Past the equivalence point, everything is still basic due to excess base, and we still have our equivalence point, but the equivalence point in this situation, since you're working with a weak acid, when that weak acid's gone, you now have a basic solution. So you end up with a pH at the equivalence point that's greater than 7. All right, so key points on both of these, excess acid. In fact, I might as well just label these things while we have it handy. So this is an acidic region. You got excess, strong acid, and as you move to the right, some neutral salt. Over here you've got excess, strong base, and down here you still have excess, strong base, but over here you have excess, weak acid with a basic salt. And we have this super duper important thing on here that we could call the buffer region. I don't have a good color choice for this. So right here we have a buffer. And halfway to the equivalence point is actually a good point on there. That's where pH equals pKa, halfway to the equivalence point. Alright, anyway, that's material for another video. All I want to do right now is just run through the stoichiometry of a stepwise titration. I'm going to do it in 2 different ways, and I'm going to try and knock these out super quickly. The first way is to think of it as starting at the beginning and adding a total amount of base. And the second way I'm going to look at it is looking at it as successive additions. And it doesn't matter at all. It's personal preference for you or how the question has been phrased. The problem we're going to look at, or the example we're going to look at, is just one where we've got, say, in fact, let's line this up. We've got 0.20 molar acid, whatever it is, some generic acid, HA, doesn't even matter, strong or weak. And we're going to titrate with NaOH, and we're going to add it in these amounts, 0 moles, then we're going to go 0.05, 0.10, ... to 0.40 moles, all right? And you can think of that as successive titrations or continuously adding to that original amount, and it doesn't matter at all, all right? So let's set this up. When you have HA titrated with, or when you have an acid and a base, it's essentially the same reaction every time. You don't necessarily get a pH 7 when you're done, but it is the same reaction every single time. And so that's going to be your acid plus your base. And if it's NaOH, we're only worried about the OH minus. And it's going to give you, in this case, A minus plus H2O. All right, same deal over here, HA plus OH minus gives you A minus and H2O. And it turns out that for a strong acid, you end up with neutral conjugate, and for a weak acid, you end up with a basic conjugate, and that can affect how your pH works out and whether or not we have a buffer situation. All right, I'm going to do stoichiometry on these, and that may or may not be obvious, so I'm just going to put a little note to us here. In fact, I'll write it once and then pause and write the rest of them. All right, so what I'm about to do in this entire column is stoichiometry. And the reason I'm making note of that is because I'm doing it as if it was an ice problem, but I'm doing stoichiometry. There we go with our stoichiometry written down the side. And again, it's going to look kind of like ice, and it's a super brute force way to do stoichiometry, but you've done enough stoichiometry with the haves and the needs and the limiting excess and the excess reactant that you should be okay handling this right now. This is what we're starting with, and then these amounts are what we're starting with. So first up, I'm going to have 0.20 molar, and I guess I'll specify here, 1 liter solution with constant volume. All right, and that's kind of a cheat. Setting it as 1 liter makes the molarity and the moles equal to each other, and constant volume means that's going to stay the same. In a real situation, when you're titrating, volume is going to change, and that adds in like another half step of difficulty. So in this first step, we're going to add 0 moles of ROH minus, and then we're going to start with 0 of this, and then I'm not worried about the water. Well, there's going to be no change. There is nothing to react here, so there's no change, there's no change, there's no change, and you end up with 0.20 moles and 0 moles and 0 moles. All right, and then over here, that step would be the same. In fact, I don't know that it's worth writing, so I'll just write it is the same. All right, now, depending on how you want to think about it, we're going to do the 0.20, and I guess for this first step, it'll end up the same way. We're going to add our 0.05, we'll call that molarity, but it's moles of the NaOH, and we don't have any of that starting out. All right, same deal here, 0.20, 0.05, and then we don't have any of that starting out. We're going to look at the stoichiometry here. It's 1 to 1. I've got 0.2 of this thing, 0.05 of this thing. This is my limiting reactant. I'm going to use it all up, so I'm going to lose 0.05. I'm going to lose 0.05, and I'm going to gain 0.05, and we're going to end up with 0.15 and 0 and 0.05. All right, and over here it's going to look exactly the same. I'm going to take away 0.05. I'm going to take away the 0.05, gain it, and we'll end up with 0.15, 0, and 0.05. All right, those are our amounts of HA and A minus, which are going to be what determines our pH when we're doing our actual calculations. For right now, though, I just want to set the stoichiometry up. And in the left-hand column here, I'm going to do this just brute force, starting with the same each time. So we'll do this successive. And over here, we will do this to the original. Okay, we'll call it add to the original. All right, and that kind of breaks it down into the two types of ways things might be given. In this particular case right here, we might say add 0.10 moles to it. All right, so we got 0.10 and, 0.20, 0.10, and 0. And so when we lose this, we're going to lose 0.10. We're going to lose 0.10 because the NaOH is still your limiting reactant. You're going to gain 0.10, and you'll end up with 0.10, 0, and 0.10. Okay? So we just started with this 0.2 again. Now, if you look at this a little differently, sometimes problems will say successive additions of like 0.05 moles of NaOH. So instead of starting at 0.20 again, we might start with the 0.15 and 0.05 again, and we had 0.05 right there. And then when you look at that stoichiometry, we're going to lose our limiting reactant minus 0.05. We're going to gain, we're going to lose that 0.05, and then we're going to gain 0.05. And you'll notice we still end up with 0.100 and 0.10. All right? So we're either taking more from the original amount, or we're doing it step by step by step, 0.05 at a time. Doesn't matter at all. The math works out the same. The equilibrium works out the same. But sometimes the problems are asked differently. So just a quick glance at how the rest of these might go. 0.20, right? And then 0.15, 0.20, and 0.20, 0.20, and 0.25. And this is where things start to get a little interesting. 0.20 and 0.30, 0.20 and 0.35, 0.20 and 0.40. All right? And this is going to be a big factor in how our calculations are done. Now, how are things going to be different over here? Well, over here, we need to carry that previous value down and just add 0.05 again. Let me make sure we're on the screen here. We've got 0.10 and 0.10, and now we're adding 0.05 again. So at each step, we're adding 0.05. In fact, that's okay right there. We've got losing 0.05, and then losing 0.05, gaining 0.05, and we end up with 0.05, 0, and 0.15, right? And then over here, similarly, we lose, in this case, 0.15, lose 0.15, and then gain 0.15, and we end up with 0.05, 0, and 0.15. Same answer, different way we're getting there. Again, each time we're starting with the 0.2 and adding whatever the total increment is at that point in time, instead of just adding them incrementally right there. And you'll notice I stopped right there, and hopefully I stopped in time. But let's see what we've got here. 0.05 from the previous, 0.15 from the previous. How are things going to change? Well, I'm going to lose right here, 0.05. And instead of having limiting or excess right here, I have stoichiometrically equal amounts. And so that puts us in a special place in the titration. In fact, this is our equivalence point. So I've got 0 there, and 0 there, and 0.05, sorry. I've got 0 there, and 0 there, and 0.20 right there. Similarly, right here, I'm going to be taking away 0.20, stoichiometrically equal amounts, and I'm going to end up with plus 0.20, and that is 0 and 0 and 0.20. All right? So at that step, we are at the equivalence point, and my color options are somewhat limited here, but I'm going to that is where we are at that point. And so you'll notice when we have the most acid, it'll be the most acidic, and then we're losing acid, it's going up, it's going up, it's going up. Then we hit our equivalence point, which will either be at 7 or somewhat higher than 7 at 25 degrees Celsius for a weak acid, and then something special happens here, and that is we use up our acid, and we now have excess base. So if you look right here, and I am intentionally changing our color coding, HA becomes our limiting reactant, and OH minus becomes our excess reactant. So we're going to lose 0.2, and we're going to lose 0.2, and then we're going to gain 0.2. The amount of salt we make stays constant, but now we end up with 0 and 0.05 and 0.20. All right? And then over here, we're going to pick up where we left off with 0, and now we're adding another 0.05, and we had 0.20, and we're going to be losing 0 of this, right? And we're going to be gaining 0 of this, and we're going to be gaining 0 of this, and so we end up with 0, 0.05, and 0.20. Again, it's just how you view that situation. Should have done blue. Let me just fix that real quickly. If you're wondering why I'm trying to go lose base in blue, end up with acid in red. Lose base in blue, end up with acid in red. Lose base, should have done red, see? Lose base, end up with acid in red. Lose base, end up with a neutral solution, should have done green or something, and then lose acid, and we're left with base. And again, let's just knock this out real quickly, and then we can move on to the other two videos for this. In this particular case, our limiting reactant is still that acid, minus 0.2, in fact, minus 0.2, minus 0.2, right? And then over here, similarly, plus 0.2, and plus 0.2. Minus 0.2, since that was our limiting reactant. And then we end up with 0, 0, 0, 0.2, 0.2, and 0.2. Our amount of salt isn't changing, our amount of acid isn't changing because it's gone. We're just getting more and more excess base. And that's why our pH starts increasing and then plateaus there. Alright, so that is what we end up with there. And if we look at the calculation right here, we've got 0.05 that we're going to, 0.10 that we're going to start with there. And then 0.20 right there. So I had 0.05 and I added that extra 0.05. So it's going to be minus 0 in this case, plus 0, plus 0. And then we're going to end up with 0 plus 10, 0.20. Alright? And this is going to be minus 0 again. I might as well just keep going through the motions. 0, 0.15, 0.20, 0.20, 0.20. Minus 0, minus 0, plus 0, minus 0, minus 0, plus 0, 0, 0.15, 0.2, 0.20, and 0.2. Alright, so what are we really looking at here for the future videos? We're looking at these numbers, alright? We're looking at where we start. We're looking at each increment after that. We're looking at the equivalence point. That's a super important one for us. And then we're looking at how things calculate when we have excess base. All right? So we'll do these calculations with these numbers for a strong acid and strong base titration just to see how things work out.